Oh wait, no, it's private. Wait, how do I turn this into public? How do I turn this into public?
Great question.
Wait,
It says Maple 1B Workshop 2025 person.
yeah.
Okay, I'm gonna head to my lecture now.
Yep. Hi.
Okay.
Bye bye.
Good luck, guys.
My fault. My fault.
All good. All good.
Seminar part 1.
Okay. The only thing is.
Wait.
Oh no.
Wait. Public.
Are you live? No.
What's happening? Wait. Is it on?
Huh? No.
Oh yeah.
Wait. No. Wrong one. Okay, let me just like refresh.
Wait, you can use my computer on the side. You can use my computer on the side.
Oh yeah. Oh.
Wait,
Like,
are you gonna
yeah,
upload-
okay.
Give me like 2 minutes. 2 minutes. Yeah.
Wait, you know, are you gonna have a scroll on the iPad?
What do you mean?
Like on the iPad, you're just gonna scroll to each side, like scroll downwards.
Yeah, just scroll downwards.
Yeah, bet. How can I answer questions?
You just hop onto the stream, and like
Yeah, but aren't you using a laptop?
Oh no, you can hop. Oh no, I have it on my phone as well.
Oh.
Yep.
Yep,
Can you drop to here? Yeah, can you drop to here?
Yeah, no, I'll do the question. Yeah, I'll do that question
just
as
do
well.
that question, thank you. Oh, you're gonna use, okay. Hey Tom, you sit. I don't deserve to sit.
Huh?
You can
I'm not gonna be there. I'm gonna be there. I'm gonna be in the back. I need to do my assignment. It's due in 3 hours.
Wait, do I have to do anything?
Huh?
Like when I teach, what do I do? I just click
Wait,
run. I just,
can you show me what the stream looks like?
Yeah. It's looking like this right now. Oh, sorry, that's looking weird. It might be because this thing is frozen.
Hey, you want a
right
calculator? I think you're gonna need a calculator. I got your calculator.
How do I turn this off?
Yeah, it's working. Okay.
Wait, how? Hi.
Hi. That's it.
Alright, great. Everyone, wait, one sec.
Wear
Oh,
these guys.
I need to wear this.
Yeah. Yeah, okay.
Oh
Put in
wow.
your pocket.
Wow, this is very high tech.
Yeah, just put in your pocket, yeah.
Alright,
Whatever.
Alright, great. Everyone, thanks for coming.
Sign in to. Oh yeah. Just in case the people are like online.
Yeah. Before we begin, before we begin, like, camp is soon. Do join. When? Week 2, term 1. So Friday, Sunday. Go to MathSoc rubric. It's last release, $209, I think. And then yeah, why join? Because it's super fun. But why not? All right. Before we begin, can everyone please fill out the attendance form so we get cool numbers.
Oh yeah, I need to.
I should.
Oh, you're all doing that.
Shoot. Are people online doing it as well?
Accounts.
Pardon?
Yeah.
Wait, if you're online, can you like do it as well?
Are people
So-
online?
I don't know. Are people
Check
online?
wait, you check the numbers.
There's like 3 people. What the fuck?
Wait, you work at Doctor Who?
That's my doctor to student ID.
What? Wait, that's a thing?
Oh, they added it. It's like relatively new. It's like they did it when I was in year 12.
Wait, why? Why? So like
It's because they want to.
Wait, that's so
They
crazy.
check it whenever you do the quiz. So yeah. They check it whenever you do the
Wait,
quiz.
you're
Right
right, so
before you do the quiz.
I thought like beat the system. My strategy is like C to A1, right? What you do is like you do the test, but then if it's too hard, you don't do anything. You just like pretend you're doing it, and then you just give them like a blank sheet, and then you go into the office, and then you say, oh wait, I want to redo the thing. I want to do it, and then just do it again because they won't know that.
Wait, it's very good.
But then now you have the ID cards that's gonna defeat the purpose. Shit.
Wait, is that very good? It's already done it?
Yeah.
It's already done it?
Just give them like 1 more minute.
Oh yeah.
How do you use this notes app?
Wait, let's not freeze the other one.
Yeah, come on in. We haven't really started, so
Yeah.
let's fill in the attendance form.
We need money.
Yeah. If you want MathSoc to have money, fill in this. Every bit of money counts.
What was starving child in need?
Yes.
Wait, do you have face cam?
Pardon?
Do you have face cam?
What?
Face cam.
Yeah.
Where is it?
Yeah. They don't need to see my face. They can see my face. All right, is everyone done? Good?
Alright, now
Happy? Okay, great. So welcome to today's revision seminar. I'm Conrad. This is Justin. Today we'll be covering over algebra, and tomorrow we will be covering calculus. Well, 2 other people will be covering calculus. So we have Ainsworth 102. Wait, can I settle down a tiny bit? Yeah, thanks. Oh, thanks, Thomas. Right, great. So today I'm gonna start with introduction to vectors and vector geometry, and then Justin will take over with matrices and complex numbers. Great. So let's get started. So algebra. So what is a plane? So a plane is essentially if I have this is a plane. So this is a plane essentially. So everything we see with a flat surface. What? One sec.
It's not.
Is that not working? Wait, sorry, one sec. Wait, one sec. The online stream isn't working.
Is it because it's
Wait.
frozen or something?
No.
Like the online stream isn't working. But the face cam is working.
Yeah. No, I think it's just the What do we do before? Wait, instead of window capture, shouldn't it just be application? Oh, display cap. Wait.
Yeah, that's what I thought, but
Oh. Oh, display.
wait, it's
Yeah, try. I think it works. Yeah.
This frozen. This frozen. Oh no,
No.
it's all right.
I think it works. Go back.
Now what? Do you open Zoom?
Yeah, he opens it. Let's see.
Is it? Oh, there's the delay.
Okay, but like fix the thing. Oh, it's because kind of like. Wait, just the wait for the. Okay, good enough.
Yeah, good. That's good enough. Okay, great. So let's get started. Sorry for the delay. Okay, so what are planes? Planes are essentially if I have a vector A. So imagine this are my free x, y, z plane. X, actually it's probably the other way around, but who cares? All right. So if I have plane here, so x, this would be A, and I have 2 vectors. So this would be the span on my plane. So v1. V2. This would cover so this plane would be parallel to all of A as along V1 and V2. So and this will be the equation of a plane, and this would be called our parametric form. So an example would be, for example, x. So x would equal 1 2, 3, plus lambda 1, 4, 5, 6, plus lambda 2, 7, 8, 9. So, and lambda 1 and lambda 2 must be real numbers. So you can't do just like 2 of these. So like 2, 3, 4. This is not plain. Right? Okay, great. So, and these two vectors must not be parallel. So because if I have two vectors that are parallel, this would be like this, and this would just be a line, not a plane. So it has to be like this. Great. So any questions? Good? Nothing? Okay, so there are also different ways where we can represent the equation of a plane. One of these is called the point normal form. So the normal of the normal plane is just a vector that is perpendicular to our plane. So imagine if my phone is my plane, a normal would be like this. So this would be perpendicular. I don't know if you can see it online. Great. Okay. So, and one of our properties, because we'll cover this later, one of our properties is like if two things are perpendicular, the dot product would be 0. So that's why our normal times a xy. So imagine x is here. So imagine here. Oops, okay, so imagine x is here. This would be x minus a. So this would be n dot x minus a would be 0. Great. So, and this is also how we can also represent this in if it's a 3-dimensional. That's what we can also represent it as. And if this goes to an nth dimensional, so like this would go to ax1. It would be like lambda x1. Actually, no, let's say mu1 instead. Mu1 plus mu2 x2 goes all the way to mu n xn. Great. And these have to be constants as well. And this can't be 0. So what this means is that A can't be equal to B, can't be equal to C, can't be equal to 0. So all of them can't be all 0 at the same time. So great. Can people I'll give you 1 minute to try vibe this out first, and then I'll go over it in a tiny bit. Great. Let's do this. So what we can do is we can let x2 to be lambda and x3 to be mu. So this way they can be whatever we want, right? So in a way, so we can just do 2x1 plus 3 lambda plus 5 mu equals -7, and we can just do 2x1 equals -7 minus 7 lambda minus 5 mu x1 equals and then we can just represent this in x equals x1, x2, x3, right? And that's equal -7 over 2, -7. Oh my god. Sorry, my handwriting's horrible today. Okay, wait, I have more space. So, and because we can just separate out, right? Because if I have 1, 2, 3 plus 4, 5, 6, we can just do 1 plus 4, 2 plus 5, 3 plus 6, right? Sorry, it's so hot in here. So this would just equal, I can just separate out, so -7 on 2, 0, 0, plus lambda, -7 on 2, 1, 0, because there's 1 times lambda, and then I can do mu times -5 over 2, 0, and 1. And this would be our parametric form. But one thing's missing. What's one thing that's missing? I need to add at the end of this. No seconds. choice. Alright, we have to specify that lambda and mu, they must be real numbers, right? Because otherwise, what if like I say like if I don't specify it, I can just say like lambda is like 2, 1, 2 or something, and that should just be a cross product instead of a constant times not a constant, a scalar times a vector. Great. Any questions? Good? No? Okay. Any questions online? Are there anybody online? Okay. Okay, there's nobody online. So, all right, great. So, yeah, here's a solution of like of a much nicer solution, I guess. Yeah, great. So that was just a intro to like how we can get from a Cartesian, so from here back to here, and now let's find actually how to make an equation of a plane. I will give you guys like 1 minute to try this again, and I'll quickly do it and speed things along a tiny bit. Okay, I'll get us going then. So let's first say this is OA, vector OA, this is vector OB, and this is vector OC. So if I tell you that in my plane, say this is A, this is B, and this is C, right? So that means every vector must like expand in like this format, like in a version of this. So it can go like here, and then here, or some combination of it, and that covers the entirety of my plane, right? So a good way of we can doing this is we can say imagine this is RA, and this AB, AC, right? So a good way you can say this is our equation. So let's say random x. So x, the vector x would be any point on our plane, would be OA plus lambda AB plus mu AC. Good. And once again, lambda and mu are real numbers. Also, this definition of a plane, so anything above this, so this bit, this applies for planes of any dimension, so it doesn't have to be, well, 3-dimension or above. So if it's 4th dimension, this would be the same thing. But this, if you move up at 1 dimension, you have to plus in something x4. Great, okay, so let's back to this. So how we do it, so if we have OA, so let's figure out what AB is first. So AB would just be OB minus OA. And that just equal 8, 3, -7 minus 4, -9, and 1. That's 4, 12, and -8. And AC is equal OC minus OA, and that's equal -6, 5, 2, minus 4, -9, 1. And that just equals -10, 14, and 1. So if we substitute this back into here, so here goes to here, and here goes into here, what we have is, so this will be an x, so x is any vector lying on our plane, would be x will equal, what's OA? OA is 4, -9, and 1, plus lambda, 4, 12, -8, plus mu, -10, 14, and 1, where lambda and mu are real numbers. So that is how we do it. So in general, if they give you like 3 points on a plane, what you do is you just simply let one of them to be A, and let one of them to B, one of them C. You set one of them. So in this case, I set A to be our original point, so here, and then our spans to be AB and AC, and then you just add them together, slap a constant in front of it, and we're done. Great. Okay, let's move on. So now I mentioned what happens if my spans are the same, are parallel. So what happened is you form this, right? So instead of being like this, it'll be like this now, and that's why we form a line. So in the nth dimension, our definition of a line will be x equals, so x will be any vector lying on our line. So x will equal a plus lambda v, and we call this our direction vector. And this to be a point vector. So A will be any point on our line. So they'll give you, given this point is on the line, find the direction, and then they give you direction, so you find a line. So A would be a point vector. Great, and once again, lambda is a real number. So here is a past question from 2020. So let's see, 1 minute again, and I'll quickly go over it. Yeah. Oh yeah, for sure. Well, actually, that might be a play. Hi, great. I'll start going over it now. So if I have any, because x, y, z fulfills the coordinates of any, so this vector x will have coordinates x, y, and z, right? So we can just say let's say x will equals x, y, z. So these will correspond to things here, right? And so this also equals to here, right? So let's just turn that into -1 plus 2 lambda, 2 minus 3 lambda, and 3 plus 4 lambda, right? So let's just say, since if I have two equal vectors, that means the x component is equal, the y component is equal, and the z component is equal, right? So that means x equals -1 plus 2 lambda, and at the same time y equals 2 minus 3 lambda, and z equals 3 plus 4 lambda. Good. So because right now we have so many things, right, running around, our end goal is to substitute this back into here. And so right now we have 3 variables here, and if we substitute this in, we just have 1 variable, right? So let's substitute in. So it will be 9 times -1 plus 2 lambda plus 4 times 2 minus 3 lambda minus 3 plus 4 lambda equals 0. And if we expand this, this gives us -9 plus 18 lambda plus 8 minus 12 lambda and minus 3 minus 4 lambda equals 0. And this gives us lambda equals 2, right? And so once you have this, that means if I substitute this back into here, this will give us the point on our line, x, right? So let's do that. So x would equals -1, 2, 3 plus 2 times 2, negative 3, and 4. So this gives us 3, negative 4, 11. So can I just leave my answer at this point? Hands up for yes. Hands up for no. Okay, the answer is no. The reason is because the question asks for an intersection, right? That means that you're looking for a point, not a vector, right? So if you leave it as like this, well, if you put it into your Mobius, it will come as a no, and you lose a mark, and that's not good. So instead, what we need to do is we need to put it into a point form. So the point form will be 3, negative 4, and 11. Good, and that will be our answer, rather than the vector 3, negative 4, and 11. Great. Good. No questions? Questions? All good? Okay, let's move on. Once again, here's a solution. This will all be uploaded to MathSoc website. So if you guys missed out on something, just go check it out, or you can go watch back the stream, which is still on. Great. So yeah. Great. So actually, let me put in an extra. Great. So dot products. So what essentially a dot product is say I have two vectors. Let's say A equals A1, A2, A3 goes all the way to AN. So this would be, and B will equals B1, B2 goes all the way to Bn again. So that means A and B are both vectors in the nth plane, right? Nth dimension, not the nth plane. So nth dimension. So if I dot product these two together, what I essentially do is I add up each of the components together. So that means the first component I just times together, and then I add the second component times together. So how we write it is like if I take a summation in n from like I equals 1 of AI times BI. So that just equals A1 times B1 plus A2 times B2 plus all the way to AN times BN. Great. So, but there's also an alternative definition of a dot product, and that is this also equals the magnitude of A times the magnitude of B times the angle between them. So say this is A and this is B. This would be our theta. Or conversely, you can also think of this as theta, but why would you? Because that's an ugly number. Yeah, so anything above would be 180 would be ugly. So, but if we let this definition to be, so if we're trying to find the angle between two vectors, we would do cos theta equals A dot B over the magnitude of A has a magnitude of B. And this will give you a theta, but theta by convention we only write it in between 0 and pi. So please write it in radians. Don't write it in degrees, unless they tell you to. Yep, great. And then so what if theta equals 90 degrees? So what if they are perpendicular or orthogonal? Some people might say for perpendicular is usually what we say for if it's in a 2D plane. So orthogonal will be anything above it. So so if cos 90 degrees, that will equals 0, right? So that means if two things are perpendicular, so if A is, right, that means A dot B would also equal 0. So that is one of our little cool tricks that we can use. So so yeah, that gets us done that, we've done that, and we've done that. So one or two little good inequalities pop up when we use the dot product. First one being Cauchy-Schwarz. But I guess this is not exact. Actually, this is one. So what Cauchy-Schwarz is saying is A dot B will always be less than the magnitude of A times the magnitude of B. That's because if we look at this here, we can decompose A dot B into, So magnitude of A times the magnitude of B times cos theta, right? Times. So, and that just means, because these two will always be positive, times the magnitude of cos theta. And cos theta will always be less than, the magnitude of cos theta will always be less than 1, right? So that means I can just turn into this, right? Another little cool inequality that we have is the triangle inequality. Triangle inequality. So say I have my little triangle here. My little triangle here. So if I have A here, and if I have B here, this will be, wait, actually no, let's swap around. Here is A plus B, right? And by our usual triangle inequality, that means my two sides must be greater than my other side, right? Or else it would just be like a flat line, and that's not really a triangle, if you think about it. So yeah, that would just be a line, right? So that means, but the point is, it can't be less than it, right? Because if it's like this, okay, let's draw it out. If it's like this and it's like this, that you can't make a triangle or like a line out of it, right? Because like if you like bring this down, it'll become like something like this, and that's not a triangle or a line, right? So what we say is A plus B. So the magnitude of A plus B must be less than or equal the magnitude of A plus the magnitude of B. And that's just our triangle inequality. There's like a fancy name for it. It's like Mercalli-Schutz inequality or something. Don't worry about that. Yeah, I forgot the name. Anyways, so here's a little good application of dot products, which I will once again give you guys 1 minute to do, and then I'll give you guys the answer. Oh, a good like trick when doing like these problems is like draw the diagram. Like it would make your life way easier, especially with vector proofs or something. Like yeah, draw the diagram. And like let your side sometimes like let a few of the sides to be like A or B, and then like that will also make your life way easier, rather than like bashing it out with unknowns. All right, great, I'll get started then. So, as I said, draw a diagram. So that's what I'm gonna do, draw a diagram. Even though it's gonna be like a very ugly diagram. Sorry, I can't draw. That's why I'm doing maths, not arts. Okay, great, so let's just say that that's my parallelogram, even though it doesn't look very parallelogram-like. So if I let this to be a vector A, so let's say this is my, well, like yeah, so this is A and this is B, so that means this would be A minus B, right? Because one of our, if I have a vector here, it will always be tip minus tail. So here, tip, that's the A, that's A here, and the tail will be a B. So that's why this is tip minus tail. Yes. And right here, and this one will be A plus B, right? Because one of our core properties of a parallelogram is that opposite sides are opposite vectors are equal, right? And what are two equal vectors? That means they are, well, they're just like equal in direction and magnitude. So that means this will also be B, right? And so you'll add this plus this will give me A plus B, right? So I also know that, so the magnitude of A would equals 1. So this will be 1, and this will be 3, right? And also the magnitude of B would also equal 3, right? So it says lengths of both and square each length, so both diagonals. So that means the length of A plus B squared minus A minus B, the magnitude of A minus B squared. This will get to 6, right? But a cool little property, once again, of if I have like x plus y and I square it, that will equal the magnitude of x plus magnitude of x squared plus the magnitude of y squared plus 2x dot y. That's a cool little property. So that means it will be magnitude of a squared plus magnitude of b squared plus 2a dot b minus magnitude of a squared plus magnitude of b squared minus 2a dot b, and that will equal 6, right? And so once we like expand our brackets, so let's take this out, let's turn to a plus. So this cancels out, and 2 plus 2 is 4, surprise. So 4a dot b will equal 6. Are you follow? Good. Right, so that means a dot b, so using our definition off the top, magnitude A, magnitude B, times magnitude B, times the, so we're trying to find this, right? This theta. Right, so cos times cos theta would equals 3 on 2, because like 6 divided. We just move the 4 over to this side, becomes 6 over 4, and that's 3 over 2. Yeah, and so that's 1 times 3 cos theta equals, let me just try to make this bigger, equals 3 on 2. And that becomes cos theta equals a half. And what's cos theta equals a half without using a calculator? I don't know, so I'm gonna look at the answers. That's theta equals pi on 3. Not like, don't write like 4 pi on 3. No, I can't do maths. 5 pi on 3. Always write pi on 3. Always, because like that would be like this angle, and that's not exactly what they're looking for. Great. Any questions? No? Nothing? Good. All right, great. Let's move on. Here are the solutions again. If you care to, they use 60 degrees, but don't use it. Don't use it. Pi on 3. Great. Okay. So now let's move on to cross product. The cross product is a little like foreshadowing to matrix multiplication. So this is essentially a 3 by 1. Yeah, it's kind of like matrix multiplication if you think about it, but not exactly. Justin will tell you more about matrix multiplication. So what the cross product gives us is if I have a vector A given by A1, A2, A3, and a vector B given by B1, B2, B3. If I cross product those two, this will give me a, so say imagine, oh my god, this doesn't work. Say this is my my vector A, this is my vector B. It'll give me a vector that is perpendicular to the two of them, or orthogonal, right?
If you guys do physics, it's like the same as the right-hand power rule.
Yeah.
Yeah. Physics.
Yeah, physics. Fun fact. Great. So how we actually do it is, like, you can either memorize this formula, which is very annoying to memorize, or how I do it is I take this, I do like a little cross pattern here, right? So that means A2 times A3 times B3 minus B2 times A3, and the next one would be, so you go here like this, but since nothing here, you actually go like this kind of, but like imagine like B1 is like down here and A1 is down here. So you do A3 times B1 minus B3 times A1. And lastly, for the Z coordinate, you have A1 times B2 minus B1 times A2. Great. So, but what is actually, if I take the magnitude of this, what does it actually give me? What it actually gives me is imagine I have A here and I have B here. What it actually gives me is for area, so the area of the parallelogram formed between A and B. Good. Good. Great. So now that you know this, let's give this question a quick try. And again, 1 minute, and then we'll go from there. Oops. Oh my God. Zach. Oh my God. Right. Wait. Okay. Okay, great. So I'll freeze it over there, so like you can actually have a look at question while I do this down here because there's not enough space up there. So let's do part 1 first. Part 1 asks us for CB, or CB, well, the magnitude of CB, but let's start with CB first, right? So that CB equals, so tip minus tail, so OB minus OC, and that's just equal 0, -4, 4, minus 3, 5, 0. And that just gives us -3, -9, and 4, right? And if I take the magnitude of this, if you recall, if I have like x1, x2 goes all, x2 goes all the way to xn, the magnitude of this will just equal x1 plus x2 squared all the way to plus xn squared. Great. Yep. So how we do this is we take the square root, we go -3 squared plus -9 squared plus 4 squared, and that just equals the square root of 106. But this is not the end. Well, this would be the end if we're doing on Mobius, but we're not. So we actually need to put units. So the units is units, and I'll just write U because like I'm lazy. So part 2 is asking us for the area of the triangles with vertices A, B, C. So if we drag this down, like this. Right. So manage this A, B, C, right? So as I said, the area of this parallelogram will be the magnitude of the cross product, right? Between A, and this time will mean AB, and B, and this time it will mean AC, right? Let me move this tiny bit down, so it's separate. 2, right? So and that means since the triangle here will be exactly half of our parallelogram, right? So I can just take the half of its area, right? So that means the area of ABC, triangle ABC, will just be half of our area, which is half of the magnitude of A times B. Good? So if you have A times B, actually let's figure out what AB is first. And AB is I'll just like, it's just OB minus OA and OC minus OA. I'll just quickly do this. -2, and 1. And 7. That is 7. And that's 1, 7, and -3, right? So let's cross product these two. So A cross B, that would just be -2, 1 times cross 1. So let's do our little X thing, right? So let's do this, right? And that would be -2 times -3 minus 7, 1 times 1 minus -3 times -2, -2 times 7 minus 1 times -2. Everyone follow? Know that? Yep, good. All right, great. So, and that will give us -1, -5, and -12 if we like do the maths. Yeah, like, this is, yeah, yeah, great. And so from here, let's put the magnitude of this into here, right? So the magnitude of this would be square root of -1 squared plus -5 squared plus -12 squared. And spoiler, that is square root of 170 over 2. Great. Okay, so there's not enough space here. So just 1 second. Yeah, great. So and then lastly, let's look at part 3. Part 3 is just if I have so they're asking for shortest distance between A and the line passing through BC. So if I have a triangle here, that is not a triangle. Yep, so if I have A, B, and C, so it will be right here, the shortest distance would be perpendicular to BC, right? That means, say, so like, we all know the formula for area of triangle, right? Half times base times height. So let's say this is D. So we have half times D times magnitude of BC, which is, let's say CB, because like from part 1, we said we use CB, right? So let's just use CB, just for the sake of it. What equals the area of triangle ABC, right? And let's start substituting things in, right? We're trying to find D. So half D times square root of 106, what equals square root of 170 over 2, and D will equals square root of 170 over 106. Good? And that just equals the square root of 85 over 53. Good? Yeah, all right, great. You. Good. Any questions? That's why drawing a diagram is good. Draw a diagram, guys. Okay, great. Okay, so, yeah, here are the solutions. Yeah, go check it out if you want to get home and do that. So, so next thing would be projections. So, the projection of a vector on a different vector would just be, so imagine I have like this. It's my vector. This is my vector, A. And if I want to project it onto this vector B, it would just be, so it would just be, I'll drag it down, so form a right angle triangle, and it would just be the base of this. So it would just be, this bit would be my projection of A onto B. So the smaller one will be what you're projecting it onto, right? So, but if I swap this around, so if I want to look at what the projection of B onto A would be, so this would be, I have to find this. this would be a 90 degrees, right? So that means I'm running out of colors. So now this time it will be like something like this, right? And this would be a 90 degrees, right? See, ooh. Oh well. Wait 1 sec. Wait 1 sec, 2 seconds. Unplug it. I think I bumped it. Alright, there we go. I want to pick up the pace because it's like, okay. Anyways, so yeah, it'll be like that, and the formula will just be up here. So projection of A onto B will just be A dot B over B dot B times the vector B, and B dot B just gives us the magnitude of B squared. So this would be A dot B over the magnitude of B squared times the vector B. And if we want the length of this, we just take the absolute value, we just take the magnitude of this, right? And the magnitude, and if I take the magnitude of this, it's B squared times B, right? And this would just cross out, and that's how you get to this formula. Great. Okay, great. So using this, we can actually find the distance between two skew lines. And what skew lines are like two lines that aren't parallel nor are they perpendicular. So like something like this, something. Great. All right. In the interest of time, I will just jump straight into the answers. So let's draw a diagram to kind of visualize what's happening. Okay, this is not the right color. So I have two skew lines. Imagine a skew. Like I know it's on a 2D plane, but like imagine a skew. So we're trying to find a distance here between the two lines. So this here will be perpendicular to both of them, right? Because they're perpendicular to both of them, that'll be the shortest distance, right? Good. So let's just say this would be actually yeah. Let's say it's just that. And then so what can we actually do to find this? And since this one here, this vector, will be perpendicular to both the lines. So what we can do to find this, let's say we call it the normal n, right? So the n will just be the cross product of the two direction vectors of the two lines, right? Because if it has to be perpendicular to two lines, it must be perpendicular to the two direction vectors, right? So let's quickly find that. So that n will equal 4, -7, 6, cross -1, 1, 3. That equals -15, -6, and -3. Great. So once we have this, so it will be this little segment, right? So it matches like the little green bit. So say I have P here, and I have Q here. Actually, let me make this a bit more dramatic. So like Q here, right? So it's like this. So if I want to find the red bit, what I do is I just project whatever I have PQ on. So I project PQ onto the green bit, right? So because it will line up, and so it will just dot it down here. So because this would be a right angle triangle, so it would just be like this. And P we can actually shift this up all the way up to P, and like that, because like you can shift around vectors, right? And that's how you actually find it. So what we would say, let's say this is P, and let's say this is Q, right? So this PQ would equals -5, 8, 7 minus -9, -7, 2, and that just equals 4, 15, and 5. Good. So let's say we're trying to find the red. So we're trying to find this little red vector, right? So this little red vector, and we already said it. The red vector. Let's say this is D, right? And we said, so we're trying to find the shortest distance. Let's say that's D. That'll be the magnitude of our D, right? And that'll just be the magnitude of the projection of PQ onto N. Great. So And that, as we saw up there, it will be PQ dot n over n dot n times the vector n. But since if we take the magnitude, this can just be our, let's look at our, this can just be our magnitude of n, right? So what's PQ dot n? That means it will be negative 15 times 4 minus 6 times 15 minus 3 times 5. This will be the absolute value of it over square root of negative 15 squared plus negative 6 squared plus negative 3 squared, right? And so that eventually brings us to 165 over square root of 270, and that takes us to 55 over square root of 30. Yes. Great. Any questions? Everyone follows? Good. Okay, great. Let's move on. So, yeah. So one more question. This is a tiny bit harder. So, I'll give you 1 minute to have a look at it, and I'll jump right in to solving it. Yeah. Yeah, I'll put the image. I'll freeze the image up there. So like, just read it. Don't need to copy it down. So. Or I take a picture of it if you want. Yeah, great. Okay, so I'll move on. So, if we look at our equation of a line, so that's another notation for equation of a line, where like that's like more like vector functional notation. So we know that our line passes through a point, let's say v equals 1, 1, 1, right? So we are trying to find, and let's say p. Let's say P is on a point on our plane. Let's say it's given by x, y, and z, right? So we're trying to have, and we remember that it's. So we remember that this will be. Oops. So we know that this little parallelogram will have area equals d. P cross V and the magnitude of it, right? But it's also, so if I have the height here, it'll be our base times height of a parallelogram, right? So instead, let's say this is D, right? So D would also equal P times V over the magnitude of V, right? Great. So what we have is, and then let's just for sake, just because if we have just a magnitude, we have square roots, right? We don't want square roots, so let's just make it d squared. Right? D squared equals p xb squared over b squared, right? So let's look at what p xb is, right? And that will just give us x, y, z, 1, 1, 1. That equals y minus z, z minus x, and x minus y. Yes, great. And so if we look at the cross product with the magnitude of cross product squared, it will be y minus z squared plus z minus x squared plus x minus y squared. Good. So, and if let's expand this, right? So, like if we expand this, so like a plus b squared goes to like a squared plus 2ab plus b squared, high school stuff. So if we do all that, we'll get to y squared plus 2yz, minus 2yz, plus z squared plus 2z squared, plus z squared, minus 2xz, plus x squared, plus x squared minus 2xy plus y squared. And if we gather like terms and keep going, we have 2 times x squared plus y squared plus z squared minus xy
Like, takes him out for an interview.
minus xz minus yz. And so yeah, let's have that. So that means d squared, and we know, yeah, so, and we know the magnitude of v, v squared would be 1 squared plus 1 squared plus 1 squared. And surprise, that's 3. Right? So d squared will equals 2 times x, so that will be, and that, if we check our equation of the plane, that's just equal to f, right? Like f, right? So that'd be 2f over 3, right? So f would equal 3d squared over 2. And that's how we get it, as required. Great. So, and carry on this last bit on vectors. Okay, great. So this last bit. So we have, so I'll just work this through and I'll quickly say. So we have x squared plus y squared plus z squared minus 2x plus 2y, 2y plus 6z plus 9 equals 0. And if we complete the square for these, because we have some x squared terms here, right? Like square terms here, and that's kind of ugly. And we also have some terms here, which makes it kind of a bit nicer. So if we complete the square, we have x minus 1 squared plus y plus 1 squared plus z plus 3 squared, and that will give us a residue of 2. Right, 2 on the other side. So what does this equation remind you of? It reminds you of the equation of a sphere. Right? So, and this would be, and our center of a sphere would just be these coordinates. So this would give us 1, -1, and -3. And let's just say this is C, right? And we know that a point, like the direct, like it goes through V equals 1, 1, 1, right? And so if I have a point and a line, the distance will kind of be given by, let's just say is D0, will be given by C cross V over V. And that's like just because, yeah, I kind of went over it earlier before. So yeah, so let's do the cross product. The cross product will give us 2, -4 and 2. And so if we take the magnitude of this will equal 2 root 6. And we also know that the V would be root 3. And so D0 would be 2 root 6 divided by root 3. And that gives us 2 root 2. Great. So if I have, like, this is in 2D, but if I have this, so if I have a center here, so the maximum distance can just be this. So this is D0, right? This plus this, right? And this would just be our radius of our sphere, right? But the minimum, so here, will be D0 minus R, right? So that means our D max would equals D0 plus R, and our radius would just be this square rooted, right? So R would equals root 2. So, and our D min will equal D0 minus R, right? And that's just 2 root 2 plus root 2 is 3 root 2, and that's 2 root 2 minus root 2, and that's root 2, right? And then we substitute it back into our equation from all the way back there. That goes to 3 over 2 D max squared equals 3 over 2 times 3 root 2 squared. That equals 27. And similar thing for the minimum that I will do. Great, okay, so great, okay. So now that's done with vectors. Any questions on vectors? Okay, I guess we want to say bye. Okay, great. So so we have that. So now let's go on to looking at matrix. Sorry. One sec. Great. Okay. So a matrix is essentially if I have a system of like say ax1, like say ax1 plus ax plus like bx2 goes all the way to, actually this is probably bad notation, lambda 1, lambda 2 goes all the way to lambda n xn, that equals to y1, and I keep going down, so like it'll be like another variable, whatever. So if I keep going down on that way, so it goes to y2 goes all the way to yn or something, or ym. If this one here, if m equals to n, this will give us something called a square matrix. So there are equal number of rows and equal number of columns. So we can turn this into something called a row echelon form. So that means, okay, I'm running out of space here. And running out of time as well. Okay, great.
That's right.
So that means we say u will be the coefficients in front of x1, right? So it will be lambda 1, lambda 2, go all the way to lambda n, and we keep going down this way using some other variable, I guess. mu1, and eventually goes to mu1, to mu n, and let's go like this, still like this, and then we let y, because this will be a vector, right? Because it's only, if we look at here, there's only like, it'll be like n things and one column, right? So we can just say it's a vector, right? So it can just be y1, y2 goes all the way to yn, and if we try to solve the equation, we would mean y. So if we try to find like what x fits in here to give us all the solutions, so y u times x, because x equals x1, x2, all to xn equals y. And so another way of we can saying this would be u, oh my god, I can't, u column y. That's our way of saying the solutions. So, and you guys use Maple, right? I assume you guys can solve this using Maple as well, so that works. So yeah, so how many solutions are there? So there are three cases. So the first one is a solution, there are no solutions if the bottom row here, so we can also write this as like lambda 1, lambda 2 goes all the way to lambda n, like this, mu1, mu2 goes all the way to mu n, column, okay, it's not straight, but you guys get what I mean, all the way to yn. And that's just, imagine we pluck all imagine we go back to here, mu1, imagine we go back to here. How we form this is actually just pluck all the x1, and all the x1, all the pluses, all the equal signs, and we just leave everything here in place. So the coefficients before the x1 to xn, and the result of our equations. That's how we find a augmented matrix. And then we can use some matrix operations where I can just like plus a constant to something, plus a multiple of some row to the other. Because if I have like x plus y equals 1, like 2x plus y plus 3y equals 2, I can just like substitute it, right? Like I don't need to like justify it, right? Yeah, so that's how our matrix operations work. So yeah, so that's how you do it. So it has no solutions if one of the rows has all zeros and has a 1, right? And because like that would mean 0 equals 1, and that's kind of not true, right? Good. And so and there's our first case. Our second case is there's a unique solution, that means there's only one solution, if and only if, that means it works both ways. Every column on the left, so every column here is a leading column. That means everything below it is a 0, right? And that's kind of what a leading column means. So, and if like everything here is a leading column, then it's done. like then that means there's only one solution. Otherwise, there are infinitely many solutions. That means like I can never, infinite. Yeah, let's get what infinite means. So yeah, so let's work through a solution, work through a question. So let's quickly do this. 1 second, I need to cheat. It's hard to make silly mistakes. Great. All right, great. So I will once again freeze over here, and in the interest of time, I will just speed run through this. Great. So the reason why I can put this through is because if I substitute all these three points into if I substitute these three things, so if I set the x coordinates of each of these, this should work, right? The x and the y coordinates, this should work, right? So so that's what happened if I substitute 1 into here, 1 into here, and here, and like 2 into the x's and 3 into the y's, and this gives us this, and this, and that's why it works. Good. Okay, great. So using Gaussian elimination, we can solve a system of linear equations. So let's present that into a matrix first, right? And so that means what we're trying to solve, x would be, we're trying to find a, b, c, d. That makes all that work, right? So that means our matrix would be, our matrix u dash y would just equal 1, 1, 1, 1, 4, 9, 2, 3, 0, 1, 0, 1, and this will be a vertical bar, 1, 1, 1. Right, and we're trying to turn this bit into every row into a leading, every column into a leading column, and that way we can find a solution for a, b, c, and yes, great. So let's try to do that. So the first thing we can let's say this is R1 and this is R2 and this is R3, right? So let's say first thing we do is R2 equals R2 minus 4R1. So that way we can just kind of turn all this into turn this into a 0, just for the sake of it, and turn that into a leading column. So that will give us 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 5, 0, 5, negative 2, negative 1, negative 3, 0, 1, 0, 1, 1. Right, it turns into something like this. So what we do next is we swap them around because we'd rather have a 1 further up than swap around a 5, right? So we swap this around. So it becomes 1, 1, 1, 1. Sorry, 0, 0, 5, negative 2, negative 1, 0, 1, 0, 1, 1, negative 3, 1. Sorry, I'm speeding through this, so my handwriting might be a bit bad. Wait, 1, 1, negative 3. Right? And so what we can do next is R3 can equals R3 minus 5R2. And so this, once again, clears this to be a 0. Wait, no. Wait, what am I doing? Yeah, what am I doing? That's why you don't speed for maths. Okay, great. So it becomes like this. So we try to turn this into a 0, right? So this becomes 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, negative 2, negative 6, and negative 8. So basically, how we try to determine this is we look at what we try to turn into a 0, right? We try to turn this into a 0, so it would just be negative 5 times whatever this. But we're also trying to keep this as 0, so that's why we use R2 instead of R1. Good? Alright, great. So that just gives us this, and so yeah. So we have found a we've kind of solved it, but as I said before, if not every single column is a leading column, that means it has infinitely many solutions. So that means I've run out of space. Okay, add page. Great. Great. So that means there are infinitely many solutions. I can't spell. Infinitely many solutions. Infinitely many solutions that can pass through both A, B, and C, right? So, what does D ask us to do? For asks us to do. For asks us, using this, find a parabola in the form. So, that means we are, let's say, so that means we have, okay, so let me just be 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, negative 2, negative 6, and negative 8. So let's just, for our sake of like our ease, let's say D equals to 1, because that just simplifies our algebra a tiny bit, because A plus B plus C plus D equals 1, B plus D equals 1, because this corresponds to A, B, C, D, and negative 2C minus 6 equals negative 6D, because if I put into 1, this all just kind of cancels out. And that also because there is no D instead. There's like we have like A, B, C, 3 variables instead, right? So we have this, and that gives us 2C. Yes, 2C equals this goes to negative 2C equals 2, B equals 0, and A plus B plus C equals 0. Right? So that means from here, that means C equals negative 1. And from here, we also already have B equals 0. And we have A plus B plus C equals 0. Right? So we're going to substitute all these back into here. And we have A plus 0 minus 1 equals 0. That means A equals to 1. And so we have our parabola. Right? Y equals to 1. Equals to x squared minus x plus 1. Yes, because if we go up here, y goes to negative 1 x squared plus, so it's something all the way back up the, it's not even there anymore. Where is it? Yeah, so back up here, A, B, C, D, back up into here. Another reason why we substitute back y equals to D equals to 1 is because we have a parabola is like y equals to ax squared plus bx plus c, right? So we need a 1 here instead of 2 or something. And we can't equal to 0, otherwise it just won't be it. So yeah, we just have this, and plus 0 times y squared plus 1 times x plus 1 times y. That's 1. And that's how we get to this, and that's how we have the answer. Great. Yes. Justin, all yours.
All right.
Oh.
How do you clip this on?
Hold it. Hold it left hand.
Wait, how do you do this thing?
I'll just on it. That's just.
Okay, guys. Can you guys hear me? Yeah. All right. Oh, okay. All right. This is the solution for the previous question. Okay. All right. Next thing we're going to move on to is transpose and matrix multiplication. If you take a look at these are the basic definitions that you have to know. First of all, the transpose. If you have A is an M times N matrix, remember that. Remember that this is the rows and then this is the columns. So when you transpose a matrix, you essentially switch the rows and the columns, right? For example, if I have A, how? I can't write.
What do you mean? No, you can't.
All right.
Yeah, no, right.
I'm clicking it every time.
Yeah, don't squeeze on. Yeah.
Okay. If we have, for example, A is 1, 2, 3, 4, right? Well, then our rows are 1, 3, 2, 4. Essentially, if we switch it, it becomes we write A superscript with a T, and then this equals to 1, 3, 2, 4, like such. So rows get switched with columns. Okay, next, the matrix product AB exists if and only if the number of columns of A, number of rows of B. Essentially, if you look at the suppose, you want n to be n equals to P. If n equals to P, then there is a matrix product that exists. Otherwise, it's not defined. So yeah, exactly. That's part 3. And your condition is n equals to P. And after your condition is satisfied, then your result, as you look in part 3, is essentially you get an m times P matrix. Yeah. So the n's, you kind of ignore them and they're just m times P. Okay. And fourth point is just how you actually do matrix multiplication. So if we look at an example here, I'll give you guys 1 minute to do this question.
Put your mic over here, because I don't think it's not picking anything up.
Okay, I'm gonna start going over this question. So first of all, you want to find P and then times by Q transposed. So what we have to do first is essentially find out what QT is. So QT, it equals to, as we switch the rows and the columns, you should get 1 minus 1, 1, and then 2, 5, 0. And we multiply, so PQT equals to 1, 2, 1, 3 minus 1, 4, and then 1 minus 1, 1, 2, 5, 0. And then to do matrix multiplication, you look at every single row, and then each row is dot product with each column of the second matrix. So first row, second row, we have first column and second column, somewhere like that. So we dot this one, and we dot it with the first column, and then that gives out a top right number. So 1, 2, 1 dot with 1 minus 1, 1, you should get 1 minus 2 plus 1, so you should get 0 on the top left. And then this here will then dot with this second column here, and then that gives out as top right. So 1, 2, 1, 2, 5, 0, you should get 2 plus 10, 2 plus 10, you should get 12. Now do it for the second row and the first column, you should get 8. And then second row, second column, you should get 1. So this is PQT. Alright. Now for part 2, the question is, what is the size of PTQ? So PTQ, right now P is 3 by 2. I'm sorry, should be 2 by 3. So we have PT equals to, what is happening? PT should be 3 times 2, and then we have Q equals to, Q is also 2 by 3. So essentially what we have now is PTQ. Well, from the definition, this would be kind of like 3 times 2 and then 2 times 3. The 2 are equal, and then so therefore it would be size 3 times 3. So your size should just be like rows and columns. Okay, part 3. Now, the part 3 question asks us does the matrix PQ exist? Well, PQ is, P is 2 times 3 from before, Q is 2 times 3. Well, if you look at this, if you PQ times together, you want these two numbers to be equal to each other. In this case, they're not, which means that there is no defined matrix for PQ. So therefore, we can say matrix product PQ is not defined. Yeah. Okay. Any questions? All right. Yeah, so these are the solutions. Yeah, okay. Next one, we're going to go through some properties of determinants. So in this case, you can take a read. A and B are two n times n matrices. Then the determinant of AB is determinant of A, determinant of B. A is an invertible matrix, which means it basically you can write it as, you can also have A equals to -1 as a valid matrix. And for part 3, if a row of A is multiplied by a scalar. Yeah, so essentially what part 3 is saying is that if we have an example matrix of like 1, 2, 3, 4, right? And then let this be A. So we can find the determinant of A equals to 1 times 4 minus 2 times 3. This is -2. Well, I can scale one row or column. Maybe I can have B equals to 5, 10, 3, 4. Right, note that I kind of like scaled the first row by 5, right, times the entire row by 5 by scalar multiple. Then my determinant of B, just calculate it normally, right? It should get you 20 minus 30 equals to -10. But what you note that is, well, the determinant of B is actually 5 times the determinant of A, which is exactly what part 3 actually says, right? So determinant of B equals to 5 times determinant of A. All right, yeah, so that is essentially a third formula. All right. All right, guys, have a go at this question.
Stream is frozen. That's fine. Don't worry.
Is there even anyone on the stream? Okay. Why is the stream frozen?
I don't know. That's what I was trying to fix. Okay, cool.
Oh, okay. All right, I'm gonna go through this question now. So first of all, we want to calculate determinant of B. Okay, so determinant of B, dt of B, we can write this as determinant of A squared minus 4A. This can then be expanded and written as A minus 4I. Now remember that I is the identity matrix. And the identity matrix is basically you have ones on the like top left to the bottom right diagonal, and everything else is zeros. They're all zeros. Yeah. And what we do now is that we can split this into determinant of A times by determinant of A minus 4I. Now we can already easily find out the determinant of A, so what we have to do now is find the determinant of A minus, well, we have to first write the matrix A minus 4I. So A minus 4I would then equal to -5. We minus 4 from like, because we have 4 of these, we have 4 here, so we just minus 4 from the entire diagonal. So minus 5, minus 5, 6, minus 8, 0, 0, 0, minus 3, minus 7, 0, 0, 0, 0, minus 3 plus k, 3, 4, 0, 0, 0, 0, 0, 0, then minus 1, minus 7, minus 5, and 0. Okay, so this is what A minus 4I should look like. Essentially what we did was like this entire diagonal here, we minused everything by 4. That's it. Okay. So what we notice here is that this is actually an upper triangular, right? So then the determinant of A minus 4I would just be equal to the entire product of that diagonal. So it's just minus 5, minus 3 plus k, minus 1, and then minus 5. This should get us negatives cancel out, you should get 75 minus 3 plus k. Okay, and also if you note the same thing, the determinant of a is actually also equal to, we can use the upper triangle to find the determinant. So the determinant of a should be equal to minus 1, 1, 1 plus k, 3, and then minus 1. And this will get us 3, 1 plus k. And so our final determinant is determinant of b equals to, well, I mean the product of these two determinants. So I can just write that as 225, 1 plus k, minus 3 plus k. Yeah. All right. And for the second part, we want to find when B is not an invertible matrix. And keep in mind, when B is not an invertible matrix, what that means is that the determinant of B it has to equal to 0, right? For it to not be invertible. So what we have to do is essentially, for part 2, let this be equal to 0. And so you can just solve this really easily. So k equals to minus 1 and k equals to 3. So these are the two values of k. All right. These are the solutions. Yeah. Okay. Next thing, have a go at this question. I'll give you guys 1 minute. No one's on the screen.
No, but like people watching afterwards, that will.
It's on his laptop.
Wait, is this yours or his?
It is his laptop. I'm not using it right now.
Okay.
I mean, the question's on both boards. That one's freeze.
No, I wanna. Why is it?
Do I just continue? Okay, yeah, I'll go through this question now. So essentially what we want to find is the inverse of A. So we can write A equals to minus 1. The formula is 1 on determinant of A. And then we can write the matrix as, should be 2 alpha minus I and then minus 1 minus I. Yeah. Sorry. Wait, hold on. Should be alpha and then 2. Yeah. Okay, and we can find the determinant of A, which is equal to 1 on 2 alpha, and then we plus 1 minus I. And then alpha minus 1 minus I, and then 2. Okay, yeah, so this is part 1. And for part 2, we want to find the values for which the determinant A squared equals to minus 1. Well, determinant of A squared, that can be rewritten as determinant of A, which can be written as determinant of A, essentially just determinant squared, right? So determinant of A or squared, and we want this to be minus 1. So therefore, determinant of A would then equal to plus minus I. Just most basic of complex numbers. So we have the determinant of A, which is defined here, 2 alpha plus 1 minus I equals to I, or 2 alpha plus 1 minus I equals to minus I. So therefore we can rearrange. You get alpha equals to minus a half, or you get alpha equals to 2I minus 1 on 2. Alright, any questions? Okay. Yeah. So here are the solutions. Okay. I'll give you guys 1 minute to do this question. So you try to simplify matrix expression. Alright, okay, I shall go to the question now. So some key things to note before we actually do the question. What is the definition of an inverse? So first of all, we have well, its inverse. This is equal to the identity matrix, right? This is the definition of an inverse. And so if I write the original thing, ATA to the minus 1, and then ATA, and then T, this is equal to, first of all, we can do this. The inverse of a product is essentially you inverse and then you inverse each of the reverse products. So I'll just write it out. So for this first thing, we can write this as A minus 1 and then AT minus 1. And then for the second one, I can write this as the kind of like the product, the transpose of a product is like the reverse of the transpose. So you can write it as AT and then AT. So essentially for both, I'm just like reversing it. I'm doing this letter first, the second one's first, and then I'll put the first one, and then I apply the top operation to both, and the same with this one. Okay, so now that we have this, what we notice is that, well, this term and this term are just inverses of each other. So we have A minus 1I and then AT and T. Note that transpose is when you switch rows and columns. Well, if you switch rows and columns twice, you get back to the original thing. So you should get A, well, minus 1 and then I and then A. And essentially what this gets you is just like I. Yeah, because it's just the identity matrix. Yeah. Technically we don't have to write the I here, but yeah, same thing. Okay. Yeah. Yeah. Okay, moving on. I'll give you guys 1 minute to do this question. But like, what is with this button? Sun. Is it even... Alright, I'm gonna go over this question. So for part 1, what we can do is, well, you just add up two matrices. So for part 1, we just have the determinant A, determinant B. Determinant A equals to AD minus BC, determinant of B equals to AG minus FB. So if you add it up, determinant A plus determinant B, well, you just get AD minus BC plus AG minus FB. You get AD plus G plus minus B C plus F. Alright. For part 2, we want to find the determinant of A plus B. Right, and A plus B equals to 2A C plus F, 2B D plus G. And so the determinant of this equals to, should put it like other way around. You should get 2A D plus G minus 2B C plus F. All you notice here is that, well, this is double the first one. So essentially we can write that, therefore n equals to a half. Yep. So I'll just write it in full. dA plus determinant of B equals to a half determinant of A plus B. Alright, and now for part 3, what is the volume of a parallelepiped? So it is essentially just, if I put my 3 vectors, I don't have space, it's fine. How do I add the next page? Okay, so we have our vectors 1, 0, 0, 0, minus 4, 0, and minus 1, 1, 2. Okay, we can put this as a matrix. Just put all the vectors as columns, so literally put them together. 1, 0, 0, 0, minus 4, 0, minus 1, 1, 2. Our volume of a parallelepiped equals to the absolute value of the determinant of this matrix. So we'll let this be like A. That's the formula for the volume of a parallelepiped. We can find the determinant because once again, this is a upper triangular, right? So because these 3 are all zeros. So our determinant of A would just be equal to 1 minus 4, 2, gets us minus 8. Volume is the absolute value, minus 8, gets us 8. So 8u cubed, I guess. Alright, this is part 3. Okay. All good? Alright. So yeah, these are the solutions. Okay. Here's an extra question, because I think I can definitely finish in time. Yeah, so have a go at this. Easy. Wait 15 minutes. Okay, I'm gonna go through this question now. So A, B, C, D has a determinant of 4. Oh, there's no writing page. Anyways, we can just, okay, so let this be write it as A, this one write it as B. We know that this one here, the determinant expression-wise, it's just AD minus BC. For B, the determinant of B, the expression we can write is 2A times 100D minus C times 200B. This is then equal to 200 AD minus 200 BC. Well, we notice that we can factor out 200 AD minus BC. Well, this is equal to 4, right? We're given that, and so this is just 200 times 4 gets us 800. Yep. All right. Yeah, that's pretty much it for matrices. Obviously, this is not the entirety, but yeah. Okay. So yeah, that's the solution. Okay, we'll move on to complex. The key thing in complex that we're going to talk about today is the Moivre's theorem. So as you can see, it is this. This is a very important thing. It only works for integer n. All right. Okay. The proof by this most commonly is by induction. Although I don't think you'll ever have to like actually prove it during a test. Okay. All right. Have a go at this question. Image is off.
After you do this one, do you want to come out for like an interview? It's for the seminar. Okay.
Anyone here do 4 unit? Oh, okay, nice. Yeah. This is pretty much like 4U content from year 12. Okay, I'm gonna go through this question now. So, part I, cos 4 theta. Okay, so what we can do first of all is write cos theta plus I sine theta to the power of to the power of 4, sorry. This is equal to cis 4 theta by the Moivres. And so what we can write is, well, we can expand this using binomial theorem. We have cos to the 4 theta, and then plus 4i cos cube theta sine theta plus, I'll just simplify it, 6, and then cos squared theta sine squared theta, and then minus 4i cos theta sine cube theta, and then plus sine to the 4 theta. This is the expansion, and then we can make this into, we only care about the real component because we want to find out what cos 4 theta is. So I'm just going to skip ahead. This is the real component, this is real, and then this is real, everything else is imaginary. So we can say equating real component. In exam, you probably like write this as like some real plus iy first, right? But this isn't, yeah. Okay, equating real component, we should get cos 4 theta because this becomes cos 4 theta plus I sine 4 theta. So we're equating the real, and then this gets me cos to the 4 theta minus 6 cos squared theta sine squared theta, and then plus sine to the 4 theta. Okay, we want a okay, so that's part I, okay? For part I, we want a polynomial in terms of, well, we have this, right? But the hint here is that we need to put our cos 4 theta in terms of everything in terms of cos, okay? So what we're going to do is, I'm just going to kind of like continue here, but this will get me cos to the 4 theta minus 6 cos squared theta, 1 minus cos squared theta, plus 1 minus cos squared theta, all squared. If you expand this, you should get, this is 1 minus 2 cos squared plus cos to the 4. You should get 8 cos to the 4 theta minus 8 cos squared theta plus 1. How do you add a new, how do you add a new page? Oh shit, never mind. Alright. Okay, so we have this polynomial. Notice that this polynomial actually looks somewhat similar to the polynomial on, like, that we're actually trying to find the roots of, right? Because the factors are somewhat similar. But what we can do is that, because it's not perfectly similar, we have to do a transformation. So what we can do is we can say that, well, if we let x equals to a half cos theta, well then, if we have p of x equals to 128 x to the 4 minus 32 x squared plus 1, well, p of a half cos theta actually perfectly equals to 8 cos to the 4 theta minus 8 cos squared theta plus 1. This just gets me cos 4 theta. Alright, so now basically by factor theorem, right? If we have cos 4 theta equals to 1, then x equals to a half cos theta are the roots of the equation p of x. So, this should be a 0. Yeah. Okay, now we basically just solve cos 4 theta equals to 0. So we have 4 theta equals to 2n plus 1 on 2 pi. That's the general formula. We have n equals to 0, 1, 2, 3. Because we do 0, 1, 2, 3, we start from 0, we go up by 1, we only need to do 0, 1, 2, 3 because there are only possibly 4 roots. Because it's a degree 4 polynomial. Okay, can you make me a new page? Facts. Okay. Okay, so now we continue. We simplify theta equals to 2n plus 1 on 8 pi. N is still equal to 0, 1, 2, 3. So we can write this out fully. We get pi on 3, 3 pi on 8, 5 pi on 8, 7 pi on 8. So therefore roots x equals to a half cos pi on 3. Oh, sorry, this should be 8 pi on 8, a half cos 3 pi on 8, and the other two roots. Okay, yeah, that's pretty much it. For pi I, we want to find what sine pi on 8. What do we want to find? Sine pi on 8, sine 3 pi on 8, what that is equal to. Now, for any type of this question that you'll ever see, most likely it's going to be Vieta's, pretty much always Vieta's, and some trig manipulation, which in this case it is. So what we have to do here is
Just walk it through. Oh,
yeah, alright, we'll continue quickly. Okay, so what we want to do is we want to use product of roots in this case. So if we use product of roots, we have a half cos pi on 8 times by a half cos 3 pi on 8 times by a half cos 5 pi on 8 and then a half cos 7 pi on 8. And then we should get equal to 1 on 128, because remember, product of roots is the constant term on top of the leading coefficient, right? And make sure to account for the negatives. In this case, it's a quartic, which means that it's going to be positive. It's not negative. Okay. Simplifying this, we have cos. I'm just gonna write. I'm gonna write like this, right? But you guys know, like, each one is slightly different. This should get me 1 on 8. Okay. Now take note of this. We have this complementary identity, right? Cos theta is just equal to sine pi minus 2 minus theta, pi on 2 minus theta. So that means cos pi on 8 equals to sine 3 pi on 8. And cos 3 pi on 8 equals to sine pi on 8. Cos 5 pi on 8 equals to minus sine pi on 8. And then cos 7 pi on 8 equals to minus sine 3 pi on 8. Okay. What we can do now is basically we substitute this all into here. And then we should get sine 3 pi on 8, sine pi on 8, minus sine pi on 8, minus sine 3 pi on 8, and then this should get us 1 on 8 like before, and then therefore the negatives cancel out. Sine pi on 8, sine 3 pi on 8, all squared gets us 1 on 8. So therefore this thing equals to 1 on 2 root 2. Note that sine pi on 8, sine 3 pi on 8 are all in the first quadrant, so it's positive and you don't take the negative. Alright. quickly go through the last question. Yeah, this is the solution. Quickly go through the last question. This question is interesting because there's two ways of doing this. And you actually get two variations of the same answer. So you want to find, take a look at this. Wait, okay, so I'll quickly go through this question. All right, so first of all, we know that looking at this, we don't want omega to be 1 because then it's not defined, but clearly omega is 1 is not a solution because you can just sub it in, it won't work, right? So what we can do is we can say divide by 1 minus omega to the 7, so we have this. Now what we can do is we can let e to the I theta equals to 1 plus omega on 1 minus, actually no, yeah, 1 minus omega. All right, and then this simplifies it because we can realize that e to I theta, if this is to the power 7 equals to 1, this is just roots of unity. So essentially what we have to do now is rearrange here, right? So what we're going to do is rearrange for w. So we should get 1 plus 1 minus w e to I theta equals to 1 plus w. And so we can write omega equals to e to the I theta minus 1 e to the I theta plus 1. Okay, now here's where the two methods comes in. So now that we have this, if I go to the next page, we can either do this. We can do the boring way, which is e to I theta minus 1 e to I theta plus 1 times by this, which is the same numerator, same denominator, but this obviously simplifies our working out, and then we can actually solve this. And you should get, well, e to the 0 plus e to the I theta minus e to the minus I theta minus 1. You get e to the 0 plus e to the I theta minus plus e to the minus I theta, then plus 1. You should get 2I sine theta on 2 plus 2 cos theta equals to I sine theta 1 plus cos theta. And this is essentially what you get. And note that theta, if you use the roots of unity, theta should be equal to...
5 minutes ago, fellas. It's time to make
Just quickly grab the solution.
Alright.
Don't show the other one.
So theta, we know that theta is between 0 to pi, and so 0 is more than equal to 2, and pi on 7 is more than 2 pi. So therefore our solutions are just, we have theta equals to 2n pi on 7, where n equals to 1, 2, 3, 4, 5, 6.
Okay,
Yep.
wrap it up.
All right, thanks everyone.
Yeah.
Thank you. Tune in tomorrow.